Right now, yes.
Great. Thank you, everyone, and thanks for the kind introduction. My name is Arash Takshi, Associate Professor, Electrical Engineering Department, South Florida. And today, I'm happy to share with you, some of the great work we have been doing regarding designing hybrid devices for solar energy harvesting and storage. But before that, when I was listening to Dr. Let's see that how I can move to the next slide. It's not going anywhere. So I have a technical problem. Okay, here we are. Yes. So just an introduction that our university is in Tampa, Florida. And I was checking Dr. Zhuang's screen and then figured out that the temperature up there is 3 degrees Fahrenheit. We are very lucky that we have 73 degrees Fahrenheit here, so quite a warm place and a very enjoyable campus. And with that, if any time of the audience coming to the Florida, let me know. I would be happy to give a tour of my lab and the group. So the picture of the students at the top are before pandemics. Now, after pandemic, now we have more students are coming to the lab and much bigger group working on several different projects. But today, specifically, I would like to share a story regarding the, the beginning of the project that ended up to new technology. We call it hybrid devices. So I'm going to talk a little bit about the supercapacitors and solar cells, and then I'll introduce the new devices, photoactive supercapacitor that we have been working, and some of the future works that we are still active on that regarding especially wearable electronics. So the story kind of started with a tragedy in 2007 when a bridge on I-35 West Highway collapsed in Minnesota, and several cars, was damaged, were damaged, and people died. And a friend of mine, a very brilliant person, came up with an idea that we could avoid problems like that just by constantly monitoring the health status of large structures such as bridges and even airplanes. And the technology that requires to do so is nothing but a simple electronic sensor with the wireless communication that can measure critical mechanical parameters such as stress, strain. We heard some of those sort of the stories from the previous talk. And if we can constantly send the data to a center, there could be sort of the process to keep eyes on the any defects in the structures, and before it become a very critical situation, they can address it for repairing. However, for doing such a job, we need to install pretty much every meter or so a sensor on the body of the structure, which means that a typical bridge may need 500 to 2,000 sensors easily, be installed on the structure. So one of the critical problem would be that how we can power such a sensor device. And, my friend started a startup company. I joined there in University of Maryland in the private sector. And we came up with the idea of having the energy harvesting through solar and then sometimes piezo to power the microprocessor and the sensor sector. And then we can, wirelessly communicate that. But one of the challenge that we faced back then was that if you look at the sample circuit, this is, of course, it's a different circuit, not the product we were working, but you can notice that the large part of the circuit is covered by the solar cell and the energy storage part, which can be a battery or supercapacitor. This is causing lots of problem for mass production of such a product. If we wanted to bring the cost down, we better to have a much compact design and much smaller footprint of the circuit. So we were thinking about that, how we can combine these two parts to one element. So therefore we can save some space. And technically, if you think about that, any sort of the solar cell approach, we usually need some sort of the energy storage to store the energy for very obvious fact that, for example, during the nights, we don't have the solar energy. So if we wanted the system to still running, the power for running the system needs to come from stored energy during the day. And the simplest design you can propose for such a combination is having a solar cell with a diode and a capacitor or a battery. So just let me address this issue that, of course, we like rechargeable batteries, and we believe that they are really reliable elements. But when it comes to systems with very low voltage for the sensors, for example, batteries are not necessarily the best solution. In fact, supercapacitors are much better because we are able to charge them from zero almost to the peak voltage. And when we use the charge from them, we can go down to almost 0 volt and consuming all the stored energy. Whereas the batteries, we have a very narrow range of the voltage for charging that. And if this intensity of the light during the day is not sufficient, we cannot technically charge the battery, and then that's a waste of the energy. So with that sort of the background, we learned that if we are going to do so, we have to look at the supercapacitor. So we wrote actually recently a very good critical review paper on hybrid systems with the solar cells and the storage part. I come back to that a little bit later again, but we have reviewed all the possible configurations and then figured out that supercapacitor are a much better option for low voltage applications. With that, for those who may not know what is supercapacitor is an electrochemical device, which we have 2 electrodes as anode and cathode, and an electrolyte. But the design of the supercapacitor is that using very porous type of the electrodes, in which we can accommodate ions inside the volume of the electrode, and based on the porosity and then the total surface area of the electrode, we can expect the huge capacitance of the chargers. And because of that, supercapacitors are now becoming more popular for energy storage, especially when we need higher power densities and fast charging and delivering the charge at a much higher rate than batteries can do. Well, as a sort of a background, a typical electrode used for supercapacitor is made of activated carbon, and that can easily give us about 500 meters squared per gram. So it's a very small amount of the material can provide such a huge surface area for ions. And as a result of such a huge surface area, we can get capacitances higher than 100 farad per gram. But this is just a part of the story. If we substitute the carbon electrodes to conducting polymers have a very special feature that they not only can form a porous structure for accommodating lots of ions into them, but also we can change the redox state of the polymers, and that would add a little bit extra storage capacitance to the devices are made with conducting polymers. So with that sort of the background, this sort of the storage devices are called pseudo supercapacitors, that we are using the redox materials as the electrode of the supercapacitors, and we can, bump up the energy storage capacity higher. However, if you look at this design, technically, all the storage is happening on the electrodes, and the electrolyte is doing pretty much nothing in terms of the storage, except serving as a media, electrochemical media for completing the cell. So we got interested in developing supercapacitors with gel electrolyte, and we started with sort of designing electrode with carbon nanotube coatings. So as Dr. Zhuang explained, there are so many features on the carbon nanotubes that can be used, especially with the good conductivity and the high mechanical stability that they have. You can put them on a piece of the paper and make a porous electrodes out of them. So we use such a design with a liquid electrolyte, sulfuric acid or phosphoric acid. And also we made the devices with a gel electrolyte, polyvinyl alcohol. And our goal of making the gel type of the device was to just making a more sort of flexible devices than liquid-based device. But when we tested them, surprisingly, we found out that the devices with the gel electrolytes are showing much higher capacitance than the one with the liquid one. If you're familiar with the concept of the diffusion of the ions into the solution, you may expect that liquid electrolytes would perform much better than gel electrolytes. But our results was showing opposite of that sort of the feature. And we also look at the case that if we made the supercapacitors with the gel electrolyte of 1 layer or 5 layers, so technically increasing the thickness of the gel to the 5 times, the capacitance increased. So one more time, I would like to go back to this one, saying that, technically in this design, the spacing between the 2 electrodes should not make any difference. But with the gel, we noticed that it actually makes some differences. So that brought up a question that perhaps something is happening inside the volume of the gel that needed to be further investigated. And we did so, and we learned that the polyvinyl alcohol and the anions in the electrolyte can experience some sort of the redox, change in the redox state, which that serve like a pseudo-capacitive effect, but not on the electrodes, on the electrolytes. So just to conclude this section, we were very happy to see that we can use the volume of the gel as sort of the extra room for storage in a supercapacitor design when we are employing what we call it the redox active electrolyte. But getting back to the original story that we wanted to combine solar cells and energy storage, we have different technologies for solar cells: PN junctions, thin films, organic, perovskite, and of course, one very sort of famous type introduced in '90s is a dye-synthesized solar cell, which can give us up to 14% efficiencies. But the main point is that it's an electrochemical device. So a quick look at the structure of a dye-synthesized solar cell. It's again an electrochemical cell with 2 electrodes, but one electrode has a coating of the titanium oxide and the layer of the dye. And once we have the light be absorbed by the dye, we generate excited electrons that can go circulating through an external circuit and getting back from the counter electrode to the electrolyte. So again, it's an electrochemical cell, but we have some mechanism for harvesting photon, and that mechanism generates some electric charges that can circulate. However, such a device, if you stop shining the light, immediately the current goes to zero, and the voltage across the cell becomes zero as well. So you do have the power once you do have the light applied to the cell, but as soon as you remove the light, the energy is totally gone. So if we wanted to use it for wireless sensors, again, we need an external capacitor to put it over there. So many people thought about that, how to combine a supercapacitor and a dye-synthesized solar cell. And majority of them came up with with designs that we call it three-terminal devices. In these three-terminal devices, you can have basically two different cells, one for solar cell and one for supercapacitor, but they would share one electrode together. This can be done by putting cells side by side and put one packaging over them, or stack them together and still sharing one electrode between them. We look at this sort of configuration in detail in the review paper, and what we found is that even when we build the three-terminal devices, whether it's a battery or supercapacitor, still we need an external diode to stop sort of consuming the stored energy when the light is gone. And that's not necessarily solving the problem that we have for designing low power, low voltage electronic circuits with a hybrid device. But what we truly want is something, we call it a two-terminal device. So a single electrochemical device that can behave both as an energy storage and charge harvesting or energy harvesting from photons. And that came to the next sort of idea, that perhaps looking at the similarity of the structure of the supercapacitor and the dye-synthesized solar cell, we can combine them by having a porous electrode, activated carbon as a counter electrode. And instead of using titanium oxide, we use conducting polymers, which has the ability of the pseudocapacitive behavior. So assuming that the light are absorbed by the dyes, we can transfer the charge to the conducting polymers, but this would be more like a pseudo supercapacitive storage. So we took that concept and put it in practice by designing a very simple cell, taking one counter electrode, carbon electrode, and taking a transparent electrode coated with the mixture of the conducting polymer and the dye. And surprisingly, we saw that it's actually working very well. This chart is showing the open circuit voltage of the cell, but of course it's negative because of the polarity of the working electrode versus counter. But if you notice, when the cell was exposed to the light, the magnitude of the voltage was actually increased from about 400 millivolts to 430 millivolts. And it wasn't instantaneous increase of the voltage, but it was very gradual, which implies that there was some actual storage effect inside of that. And more interestingly, when we stopped shining the light, there was the voltage was stayed at a higher level, which means that there's still some energy was stored inside the cell. So also the short circuit current showed some sort of the advantage that even in the dark, you can get some current out of the cell. And just testing it as a supercapacitor with a cyclic voltammetry, the device showed a very decent amount of the capacitance for a cell like that. And even changing it to a different dye, we were able to, get a much more stable voltage after, stop shining the light to the cell, meaning that the device had a much lower recombination rate, and the charge storage stability was improved. So we look at the mechanism, and it's all about that how, again, we heard very briefly about the HUMO-LUMO structure of the material. So we are taking advantage of that for energy harvesting and storage. But investigating this diagram, we learned that perhaps the conducting polymer P.PSS that we have been using was not necessarily the best choice for that. So we look at a different conducting polymer, polyaniline, and particularly we chose this polymer because it does have multiple redox states. It can go from emeraldine to PNB or LEU mode. Depends on that if you are giving or receiving electrons from that. So applying that in the same sort of the design, making the cell with the polyaniline dye and carbon nanotube counter electrode, we saw that actually in the liquid electrolyte, we can change the oxidation state of the polymer by just shining the light. And when we have the good dye on that methylene blue, the amount of the translated harvested energy to the electrical energy would be significantly higher. And all lead us to a good point. But we were thinking about combining it with a supercapacitor with the gel electrolyte. So when we went with the gel electrolyte, we figured out that actually we are not getting very good results. And it does need to explore that why gel might work better as a supercapacitor, but not as a hybrid device. But I was lucky that a student of mine came up with a very interesting idea to say that let's design a gel that would contain the polyaniline into that. So we went for a very simple process of taking polyvinyl alcohol, mixing it with an acid, and then adding an oxidizers, APS, and then adding aniline as a monomer. And then we got the in situ polymerization to produce polyaniline. So as you can see, just by mixing different materials in a beaker in a 3 steps, we generated some sort of the colored gel, which we know that we have the polyaniline inside the gel. So we took that sort of the gel and simply put it between the 2 layers of the glassy carbon electrodes. For those who have worked with the glassy carbon electrodes, they know that it's very conductive, but it's a non-porous electrode. It's a very shiny surface. So typically you don't expect much of the electrochemical capacitance because of the non-porous structure of the electrode. But surprisingly, we saw that actually we are getting very good capacitance. And not only that, we are able to identify that the redox state of the polymer, polyaniline, is changing as we charge the device. So this is really interesting, especially after Dr. Zhang's talk that we were talking about that how we need to disperse molecules or nanoparticles inside the volume of the material. So you can imagine that if we go with beyond the percolation effect, there would be short circuit between the 2 electrodes. But if you keep the level of the nanoparticle, in this case, conducting polymers, we can reach to the level that they are not necessarily connecting the 2 electrodes, but we have a media that now we can use their properties such as energy storage there. So more importantly, we put it now in a sort of the between the 2 porous electrodes, and we got a very high capacitance. So that was a contribution of a little bit of the gel showing some capacitive effect, and also the double layer charges at the electrolyte interfaces. And when we just put this gel on the titanium oxide electrode and the carbon electrode, we could get, the hybrid device with up to 138 millivolt open circuit voltage when the light was shined on that. You can see that even if I kept shining the light over the electrode, we could increase the voltage up there, but unfortunately, my student wasn't careful enough, so it stopped shining the light, so we couldn't see even more impressive number. But anyhow, the structure is showing the concept very well. And interesting part is that, what all we are doing is that making a gel with a very simple process of mixing chemicals together. And then like, spreading butter over bread, you can get the electrodes and then put the gel over that and then sandwich it with another electrode, and you do have the hybrid device. And not only that, we learned that if we just put that the gel between the two transparent electrodes, we can make an electrochromic device, meaning that by applying, let's say, that 2 volts voltage across that, we get totally black color and opaque gel. But when you apply 0 volt, it becomes quite transparent, and you can sort of use it as electrochromic windows. But once we get to this part, we had to analyze that what exactly is happening, how the how the redox state of the polymer changes inside the volume of the gel. And we have hypothesized that it is because of the ability of the gel for conducting both electronic and ionic charges at the same time, and the interaction between these two different type of the charges can assess the change in the redox state of the conducting polymer. And once the redox state changes, even the color of the polymer changes, so we can see the transparent or the dark version of the gel. But more importantly, this is now talking about that the gel itself, the volume of the gel itself, is the media for storage and for light absorption and energy harvesting. So we took advantage of such a feature and said that perhaps we can use it for making wearable hybrid devices. And we took that sort of the gel and chose 2 different type of the conductive threads. We coated them with the gel, and then we twisted them together with another layer of the gel. You can see that in the picture at the side, that it's looking very uniform coating over the 2 threads, and it's even flexible. But having 2 different threads, we now have 2 different electrodes. So we started to testing them. And of course, we figure out that if we would coat one of the threads with some sort of the metal oxide, such as zinc oxide nanowires, we are able to improve the energy conversion efficiency in the devices. So this is a very recent result from very recent publication that we have that shows that just by sort of putting the gel between the 2 threads and then twist them together, you can make a hybrid device that generates some voltages, and when it's dark, it still can maintain that stored charge. We are in the process to sort of start putting many of them together. So by putting them in series, this 35 millivolts can be jumped to 70 millivolts, 100 millivolts, and so just by adding several fibers to be in series. Or we can put them in parallel to get sort of much higher current out of the system. So just to conclude, we learned that we can use the volume of the gel electrolyte to be as additional charge storage media for supercapacitors applications. And using redox active gels, we can have a photoactive supercapacitors and electrochromic windows. We can use this balance between the electronic and ionic charge transport property of the gel for energy storage and harvesting. But more importantly, for me and the students who are working, this is a very complex sort of the research subject that we are enjoy to do different type of the material characterizations, device optimization, characterization, and so on. With that, I would like to thank the students who were involved. A few of them have been already graduated and are serving as postdoc and professors in other universities. And also the project was funded by NSF and Florida High Tech Corridor. I'll be glad to, answer any question. Shall I stop sharing my screen?
Thank you, Dr. Tashi. Yes, please. And we have a question here. Should I read it or?
So what is the question?
Are there any new wearable technology and devices to efficiently scattering energy from the human body?
Right. Yeah, very good question. I would say that, of course, one of the challenge for wearable electronics, especially regarding energy harvesting, is efficiency. As I mentioned, we are enjoying this sort of the new field of the research, but we are very far from, making devices with a good enough efficiency. And of course, alternative source of the energy than, solar is using the heat, which, for example, the temperature of the body or the temperature difference between the human body and then the environment can be a source. But thermodynamically, if you put that sort of those numbers together, you probably expect not much of the available energy, and when the efficiency is not good enough, you may not receive reasonable enough energy. So for that, obviously, we need the thermoelectric materials, and that's another exciting field of the research that I'm looking for an opportunity to start a project like that too.
Thank you, Mr. Takshi, for your delightful presentation. Amna.
You're welcome. And so thank you. I'm going to stop my microphone and video. Thank you.